Yes, hello everyone. It's 10 o'clock today on Friday, so welcome to this small question and answer session. I hope everything works fine. We will, or my proposal is that we actually have a look at the small exercise kind of from Tuesday. There was an additional exercise posted on the slides. We can go through this exercise and then also answer more questions. Some I collected from the Canvas, and maybe there are also even more questions posted here online. So please feel free to post your question, and I will then try to answer them as soon as possible or during the session. Let's see. Okay. And yeah, Patrice and Eva, they will also join in during the session. And if there are some more specific questions to their topics, please feel free also to ask them, or they might be, of course, the ones who could answer some specific questions. Okay, I think you will now see my my screen, so we can maybe quickly go through the to this exercise here. So maybe in the first exercise I quickly showed on Tuesday, actually we had a tension joint where the connection or the doweled connections were loaded parallel to the grain, so a pure tension joint. And here actually we have a joint that is loaded in shear. Okay, yes, we will probably work on the posting the or what is it? I have to check. There are some questions coming. Yeah, so I mean this this session is recorded, but I don't know. I will check with Patrice where the recordings from the other sessions were, so then you can. But yeah, let's have a look at this task. So we have this secondary beam to a main beam connection. It could be, for example, a floor beam or some other detail, or like a bracing maybe in a whole structure, a purlin here connected. And we want to design this connection here, which is basically mainly loaded in shear. So it's assumed that this beam here is, for example, a single supported beam between two main beams, and of course this connection could be assumed to be more or less hinged in that part. We have a glulam GL30C here for the secondary beam. We want to just focus on the secondary beam here for the moment. And we have some dowels, strength class 5.6 with a diameter of approximately 10 millimeter. Again, we can, I mean, if there is no force given here, in that case, we can maybe check how much capacity this secondary beam had in this support configuration, and we calculate actually the shear strength of the beam would be around 30 kilonewton, just the shear capacity of this secondary beam at the support. And of course, maybe the loading will actually be governed by some bending stresses or by some deflections. But that would be the capacity, shear capacity that actually could be transferred, or maybe we could aim at this beam support. Again, from the material properties of the steel, we can and the density of the timber, we can calculate the embedment strength and the plastic moment of the fastener. And now we have like a connection with a single slotted in steel plate, and for that we can, of course, according to Eurocode, do the calculation here of the relevant failure mode, and we can determine which failure mode will occur. Or we can go to the Limtre handbook, and we see for, these equations here apply for depending on the timber thickness. One of these equations will apply depending on the timber thickness of this connection. Maybe this is a very general, of course, a representation of the situation. So you can calculate, of course, the tensile joint or also a shear joint with this type of, depending on the fiber angle, actually it will result in the different loading direction. This minimum thickness here is around 25 millimeter in our case, and this maximum thickness is around 80 millimeter in our case. So with 80 millimeter, we have this plastic deformation of the fastener with 2 plastic hinges, and for this smaller capacity, actually, we have the failure only with 1 plastic hinge. And our timber thickness that we have available is the width of the timber member minus some slotted in steel plate, and it's around 55 millimeter on both sides, so it's just in between. So we can use this equation here above to calculate our capacity on one side, and of course for the shear planes on both sides, and it's the double, so it's around 12 or 11.6 kilonewton on both sides per fastener. Actually, we have to look now how many fasteners we can put into this connection. So for the fasteners loaded perpendicular to the grain, the effective number of fasteners is or the total capacity can be calculated from the number of fasteners here spaced perpendicular to the grain, and the N effective here parallel to the grain, the number of fasteners parallel to the grain. If the connection is loaded perpendicular to the grain, actually N effective, and this equation is just equal to N parallel. So there is actually no reduction necessary due to splitting of the fasteners parallel to the grain. The reason is that, of course, the splitting in the direction parallel to the grain occurs only if this wedge action of the single fastener creates here this accumulation of stresses perpendicular to the grain. But of course, if the connection is loaded perpendicular to the grain, here in this case, actually the wedge action does not act parallel to the grain. So it the dowel is loading or not introducing like tension perpendicular to the grain stresses directly ahead of the fastener. So therefore, actually, for the connection loaded perpendicular to the grain, we can assume the total number of fasteners directly that we use in our connection. And we have to, of course, see how many fasteners, or we have to, of course, assure the spacing. We can look in this table here given in Eurocode 5, where actually the spacing is given independency of the load to grain angle. So we have to look actually at A2. What is interesting for us, A2 is a perpendicular to the grain spacing between single fasteners. So wait a second. I can actually. Let's see here. So if we have our connection with a steel plate here, and we load it in that direction, then we have here maybe some fasteners, and yeah, this is our A2, the spacing perpendicular to the grain. In that case, we have here some end or edge spacing, so to the beam edge, that would be A4, and we have two A4s, one on a loaded edge and one on the unloaded edge. And in this case, kind of this dowel pushes here to this loaded or to this edge, so that's our A4T. And this one here would be our A4C, so the unloaded, or maybe one could say in compression, or this one would be a bit in tension, the spacing. In addition, we have here also the A3. In that case, we don't put any load here on the edge or on the towards the beam end, so that would be A3. Oh, sorry. Let's say A3C. But here for an angle of 90 degree to the fiber, so we have to calculate our A3T in that direction. But yeah, for the calculation of our of this one row of fasteners, we do not need now the A3C. We just use, or we see how many fasteners can we put into this one row of fasteners, or this many rows of fasteners in that sense we can use. And yeah, we have these different spacing available. So if we put this in, we see that we can, or here on the unloaded edge, we have 3 times the diameter, then in between also 3 times the diameter, and here on top we have to keep 4 times the diameter, and we see that actually we can put in more or less 4 dowels, and then we have a little bit more on the top available. So we have this 180 millimeter, so it's 4 times 30 is 120, plus we have to keep here 40 at 160, and then we have 20 millimeter extra that where we could kind of play a bit around, so that's 30, so that's in total 120 millimeter. And then we have here, yeah, that's is larger than 40 millimeter, so that's here 60 millimeter. So we have a little bit of possibility to adjust our connection. So, and with these 4 dowels or 4 n perpendicular is 4, n effective, which is n parallel is 1, just one number of dowel in parallel to the grain direction. So we have a characteristic value of around 46 kilonewton and a design value of 32 kilonewton, which is larger than the 29 kilonewton, the shear capacity of this connection. When we load the connection perpendicular to the grain, actually we'll find in Eurocode 5 some additional requirements that we have to check. So parallel to the grain, the connection loaded parallel to the grain, we have some risk of splitting kind of this the fasteners are loaded behind each other. If we have the connection that is loaded perpendicular to the grain, we also have some risk of splitting. And this splitting here, it's this picture from Eurocode 5 that is actually here one beam and this other beam loaded at an angle. So we have to be careful that we don't get splitting of the beam here in that direction. So the fastener, kind of the bottom fastener in that sense, is creates tension perpendicular to the grain, stresses here in that beam that is loaded perpendicular to the grain. And we have to assure that we don't get any cracking in that direction. Another image could be like if we have a connection here, for example, with a slotted in steel plate loaded like this, and where we have maybe some number of fasteners like this, maybe in a truss structure, then actually this one is our beam height H, and this here is actually our beam height H effective, which is here this height. So it's always the row of fastener that is kind of furthest away from the loaded edge, where actually we might expect the crack to occur. The closer this row is to the loaded edge, actually the higher the risk of splitting is. If the row is very much on the top, then we have hardly any risk of failure, since more or less the load is introduced mainly due to compression into the beam. Yes. I can show another, but let's continue like this for the moment. So the equation that we or what we have to, how we calculate the capacity is actually this one here. Sorry, I have to actually I just see an error here. It's actually not the design value, but it's a characteristic value in Eurocode 5 here. So what we have is actually the resistance or the failure splitting load here perpendicular to the grain is 14 times B, and then this square root representation independency of the loaded edge distance. If we calculate this value in that situation, so we expect splitting to occur in this line. We expect that the crack might come here at this point of the beam. So our loaded edge distance is just this one here, which is 180 minus the 30 millimeter edge spacing, which is 150, and we see that our characteristic value is around 50 kilonewton, and our design value is 33.4 kilonewton, which is larger than the fastener capacity. that would be for the connection loaded perpendicular to the grain. Maybe one comment, or we can actually check it. I mean, I placed here the beam or the connection very much to the lower edge of the beam. And what would happen if you would actually put it a bit up, so that you just have the 40 here on top, so 40 millimeter from the edge and not the 60 millimeter as in the other case, and keep a little bit more spacing here on the bottom. I mean, that could be maybe a choice. Then in that case, we have actually the H effective is 130 millimeter, and our characteristic value 34 and the design value 24 kilonewton of the splitting capacity. And then we see that suddenly this splitting capacity becomes decisive for our design. So in that case, actually we might expect a splitting to occur here instead of some more ductile dowel failure in the connection. And maybe some comment also that this equation it turns out to be a little bit unconservative. So a recommendation actually would be here in that case, where we have the support of this secondary beam in this connection, to consider this actually as a notch beam to make an additional check for this situation. So one can assume that of course this beam here is actually more or less kind of a notch beam where actually we where we kind of have a it's not quite, or maybe, I mean, it's kind of this this situation where we have actually where we have a notch beam, and where the load is introduced at a certain distance from the or where we have a cutout here, kind of where the load is introduced. And then of course we will use this equation for the notch beams we saw before. And if we calculate it, we see that actually we have quite a bit lower capacity for this notch beam configuration. So in that case, actually, the splitting here in this configuration would become decisive for our beam end. So if we want to be very much on the safe side, we should actually, or we could consider this load here as relevant for our connection perpendicular to the grain at this beam end. So that would be then the governing load. I just had a look here at this secondary beam for the moment. I didn't look at the connection to the main beam. There are often the steel plate in that case. Let me see. This one here, there are typically like some prefabricated joist hangers or some concealed hangers that are, for example, nailed in or screwed into the main beam. So there are different products available on the markets. Maybe some comment that was asked before, especially this kind of this special main beam, secondary beam connectors there are often or there are quite a number of systems available where actually the slotted in plate is actually made from aluminium, so there are aluminium hangers. And then you have special self-drilling dowels where you actually just make a slot into the beam. You put the aluminium plate inside, and then you can drill in or screw in these dowels and like drill through or drill directly through the aluminium plate. And you don't have to need, or you don't need any pre-drilling of the beams, which is of course or creates a very nice connection, a very nice yeah, you don't have any tolerance, you don't have to fiddle around to find or to get the hole with a pre-drilled holes, but you can drill everything directly on site together. This, I mean, various producers have different solutions for this pre-drilling dowels. They are steel thickness is typically around 5 millimeter that you can, or where you can drill through a steel plate. And of course, with aluminium, it's a little bit more actually that is possible. So here you can also see an example of a connection with two slotted in steel plates where the dowels were drilled through the steel plates and create, of course, a very nice connection. Yes, I will update actually the exercise or the solution on Canvas. There I had a small error with regard to design and characteristic loads. I have to update. Yeah, no, I mean it's there was a question about the loaded edge in the end is like I mean the secondary beam is resting kind of on this steel plate, and of course the dowels, they push kind of upwards, and the beam pushes downwards. So actually this upper edge is actually kind of the loaded one. The bottom edge is actually there is no real load pointing towards the lower edge here in that case. Let's see if there was a question directly related now to this exercise. Yeah. There was one question about if it's possible to show how to calculate a plate for the connection column to beam. I'm not quite sure if I understand the question exactly. Which kind of, I mean, if you have of course a column and you attach a beam here, then it's actually more or less the same as I just showed. It's just not the column is vertical, and otherwise it would be a horizontal beam. I don't know if you mean like this beam here on top and the column here below, and probably some kind of connection between these two, or these two. So maybe I don't know if you could make a clarification, Joao. So the second example, I guess, is asked. Well, what you would do is of course, I mean, in this situation, actually, what you have to verify is the compression stresses perpendicular to the grain. So if the beam is resting on the column, then actually, it's just you verify the compression stresses perpendicular to the grain. And you can, of course, consider the you can look into Eurocode to find the right equation. You can assume a little bit larger contact area for the effective for the spread of the stresses perpendicular to the grain, kind of in that direction. What you could do is, if you don't, if the verification is not fulfilled, is of course to reinforce the support, for example, with some self-drilling screws, and then you can increase the load carrying capacity of this connection loaded perpendicular to the grain. I think in the LIM3 handbook there should be some examples how to calculate this capacity of the reinforced support, so that there you might find the relevant information on that. But basically it's compression perpendicular to the grain at the support that it needs to be verified here.
Jag kan kanske tillägga det Eva här.
Yes, yeah.
Det är en fråga om pelartopp, och om man tittar i LIM3-handboken del 2 kapitel 14.6, då står det mer om pelartopp. Det är som Robert säger här, det är mycket kontakttryck, men om man vill dimensionera laskarna, till exempel stållaskar eller trälaskar, till exempel om man har en horisontalkraft som ska överföras eller en lyftande vertikalkraft, så finns en beräkningsmodell här i LIM3-handboken hur man ska beräkna laskarna också. Och själva exemplet är väl uppdelat i olika delar i LIM3-handbok del 3. Kontakttrycket ligger i exemplet bara för en balk, tror jag, dimensionerar för en balk, och sen ska det finnas ett exempel med laskar också, hur man dimensionerar laskarna. Jag vet dock inte exakt vilket exempel det är. Men om ni kollar i LIM3-handbok del 2 på kapitel 14.6 pelartopp, så hittar ni lite kring detta också. Och så var det tidigare, för 2 veckor sedan kom en fråga kring, eftersom de här laskarna som man har mellan balk och pelare oftast fungerar som en gaffellagring, hur man då ska dimensionera den här gaffellagringen. Och då har Robert, den frågan finns i Canvas och uppladdat där med ett svar med en ekvation hur man kan dimensionera de här laskarna så att de ger tillräckligt stöd för att skapa en gaffellagring till en balk. Ja, färdigt från mig här.
I actually could show here an example. I mean, that might show a bit. I mean, of the reinforced support. If I maybe if you answered it already or said something about that. I think in the LIM3 handbook you find some information how to calculate actually or verify the possibility of a reinforced support, where actually by the reinforcement you can increase the effective width of the contact area and benefit or increase the load carrying capacity. Maybe a word, or let's see if that was no. Sorry. There was a question about then I mean the question about this effective height is I mean it's always kind of the I mean in this situation here the connection or I mean that would actually represent exactly the situation we are having in our example. So this is a connection in the center of the beam, but if we imagine that we have our beam here and we have these two dowels here, and we actually have like kind of the load of the steel plate here slotted in, or here an external plate that is pulling in this direction. So this H effective is just kind of this distance from the loaded edge to the most far away dowel from the loaded edge. In the opposite case, or like for if you pull it down, then it would be going into that direction. So that's the common how to define it. There was sorry, I have to keep track of the questions, but there was a question of a rule of thumb. I don't know if it's about this failure mode or another failure mode actually. Kind of one rule of thumb could be actually that typically, or in this type of connection, if the H effective or splitting becomes more relevant if H E is smaller than 0.7 times H, or that's sometimes considered as a magic bound or boundary where the splitting actually becomes decisive. What is actually the kind of, if we say look at this equation, actually F90 RK or so. If we have H E divided by H here, we have here a value of 1 when it would be like loaded on top. Actually, what happens is that it's I think it's more or less like this direction, or like the shape of this equation is actually more or less like this. So you have a lot of very low values for a long time, and then at a certain point you actually go towards more or less infinity, and of course at a certain point the splitting does not become decisive anymore, or the resistance against splitting becomes very high. Let's see. Yeah, I mean, there was a question about if how hinged or not hinged this connection is, and that depends, of course, a lot on the on the size of the connection. I mean, the lever arm, or the kind of course, we could calculate the moment that could be introduced, or the stiffness and rigidity of this connection here. If the dowels are not spaced, or I mean the height of the beam is rather small, and the spacing of the beams is also or they should be compact together in a way. And then the hinge action is actually quite or the moment rigidity of this connection is rather limited in that case. If we have of course much, or I mean one can make a study if you have many more dowels in this type of connection, that then we might actually have some rigidity in this type of connection. It probably also depends a bit on the length of the secondary beam. So of course, for very long beams, one can assume from bending quite a rotation occurring here at the beam end. Whereas for rather short beams, actually there's hardly any rotation to be expected at the beam end. So for the very long beams, of course, if from bending there's quite a rotation introduced here at the beam end, the connection might be loaded also with a certain or a certain lateral deformation might be induced into this connection here. But for if the rotation at the beam end is rather low, then actually these dowels do not impose a big moment, or are not acting very stiff in moment direction.
Jag kan flika in med ett svar på en annan fråga som är om stabilisering. Och då är det en fråga om det finns krav på minsta styvhet för vindkrysset. Och jag visade ju hur man kan räkna ut styvheten för vindkrysset om då vindkrysset eller stagningen inte ligger i direkt linje med så att säga utböjningen. Och det är då ekvation 13.1 i limträhandbok del 2. Och det är den är här i limträhandboken framtagen för väggar, men den funkar på samma sätt i i vindkryss också i taket eller i vindkryss i väggen då. Men frågan är här liksom vilken minsta styvhet ska vi ha då? Och då kan vi tänka oss att de här, om vi tänker oss ett vindkryss i taket, då ska ju det här vindkrysset också förhindra utböjning av en balk mot vippning. Och då hittar ni till exempel i den här lilla boken som är dimensionerad träkonstruktioner del 2, som är den här formelsamlingen. I kapitel 12 om stagning så hittar ni hur man beräknar minsta styvhet eller den här nödvändiga styvheten för tryckta element. Och den kan vi ta, men då antar vi att om det är en balk som är belastad i böjning, då är ju överkanten tryckt, och så räknar vi utifrån momentet, så räknar vi ut vad är tryck- och dragresultanten. Och utifrån då den här tryckresultanten kan vi beräkna vilken styvhet behöver vi för att staga. Och sen kan vi då räkna ut så att säga vad blir det översatt, vilken styvhet behöver vi sedan när vindkrysset inte ligger i samma verkningslinje som den här utböjningen. Så ni får kombinera de här ekvationerna, att ni gör en så att säga flyttar det från en pelare till den tryckta kanten av balken, att se den som en pelare. Och sen kan man använda samma ekvationer. Jag hoppas att det var svar på frågan.
Maybe just some picture here of this connection. Also, you see here the splitting of the beam here at the near the fasteners away from this load introduction with this plate. Or here an example of a secondary beams that are connected here to a main beam, and they are actually connected here on the lower edge of the beam, which of course will introduce in this main beam also the stresses perpendicular to the grain. And actually that's just half of the picture, because here on the second side or on the right side you see that actually the kind of this intermediate floor here kind of failed along the entire edge. So the beam was loaded here on the lower edge, or the connections were put in the lower edge to this large beam, and introduce these stresses perpendicular to the grain in this long beam. And situation that we of course do not want to observe or find in practice.
I can hardly hear you, Robert.
Okay, I try to talk louder here. I mean, it's just not very important. I mean, I think you see the effect of the connections that were loaded perpendicular to the grain here. Let's see. Maybe one word also that was a question that was raised last time already about I mean, in this situation we drill the dowel through the steel plate, so there's actually zero gap between the dowel and the steel plate, but of course in other situations actually we will have to or what we will do is actually to I mean, we have a timber member where we drill holes inside, and then we have a steel plate also with holes inside. and we have to put them together, and then we will insert the dowels through the holes in the timber and through the steel plate. And of course, then it's a matter of good workmanship to, of course, that this fits nicely together. What is done is actually that this holes here, the kind of drill hole diameter in the timber is actually equal or maybe slightly lower than the dowel diameter. So that's in the timber, typically the thickness. And in the steel plate, actually the thickness of the holes in the steel plate should be kind of larger than D, of course, but is typically smaller than approximately D plus 1 millimeter, or for example D plus 2 millimeter, especially if we have a hot dip galvanized steel plates. So steel plates with some zinc coating, that where actually this zinc coating is produced after drilling the holes, and of course then it's a bit of like additional layer on the steel plate. So this thickness or like dowel or drill hole thicknesses are commonly used in practice. And of course, the smaller the hole is, or the closer it is to D, the stiffer the connection will become. And if it becomes very large, then of course we have a little bit of slip between these two connections. So for a tension joint, it might be wise to actually have a very thin tolerance in order not to have a lot of deformation for this main beam secondary beam connection. We could maybe, I mean, this spacing maybe 1 millimeter slip doesn't really matter in the connection, so that's maybe not so relevant. The thickness of the steel plate, or I mean, I would say it's rather tricky actually, or most of the, depending of course on the producer of the steel plate or of the timber part, but this slit or slot here in the timber is typically larger than or in the range of 10 millimeter. So it can be difficult. It can be actually quite difficult to create a very thin slit. So depending on the machines you use, some kind of what's called grinder, or some CNC tools, or some kind of chain saw tools. The thickness then is around 10 millimeter commonly. So a typical thickness of the steel plate would be maybe 8 millimeter, so that you have a bit of 1 millimeter spacing on both sides. Or of course, for larger dowels and larger steel plates, then you will have thicker slots in the timber. Yes, maybe we can have a quick look here at this In this example, maybe there was one comment on the effective number of fasteners in the direction perpendicular to the grain. It's true that, of course, the load carrying capacity FV-RK is smaller when loaded perpendicular to the grain, but that is actually reflected here by this embedment strength perpendicular to the grain. So it's embedment strength parallel to the grain divided by this factor, so it's actually reduced by 50% compared to the parallel to the grain direction. But then once you have calculated this capacity for a single dowel, you don't have the this row splitting effect as in a connection loaded parallel to the grain. So therefore, you can apply the full number of dowels in this situation. But I could maybe go through some, or like have a quick look here to this example where we have fully threaded, or where we actually want to create this type of connection with fully threaded screws. Of course, as mentioned before, the I mean, we can make a choice of a type of screw, for example, which we can design according to Eurocode. Such an example would be given here, and yeah, we can again calculate how big the shear capacity of our beam is as a reference. And according to Eurocode 5, yeah, for these yeah, screws between 6 and 12 millimeter, and with this like inner core thickness between 0.6 and 0.75% of the outer diameter, we can actually apply these equations here, and we can calculate the withdrawal capacity of the screws with these equations. Nevertheless, there are a lot of course, producers, manufacturers who have actually more or a higher capacity specified for their products. So depending on the situation, you might want to choose maybe a specific producer and actually benefit from the higher capacities that they will state for their specific product. But anyway, we can apply the equations in Eurocode 5. We have to calculate the effective length of the screw in the timber. So in that case, it's more or less, oh yeah, it's this length here, the height of the beam. We assume here a screw arrangement under 45 degree. So we have an effective length here of around 127 millimeter that would be available, so around maybe 120 millimeter that we want to apply for the design. And then withdrawal capacity actually reduces or becomes a bit smaller with increasing diameter and with increasing length. For this situation, it would be 12 Newton per square millimeter, and with that we can actually calculate our withdrawal capacity of one screw here in one timber member under 45 degree. Yeah, per single screw. If we have the screws here in a cross arranged, again we do not account for this friction in the joint line here, since yeah, the screw in compression will actually a bit separate the two members. So in that case, the capacity per screw would be here 6.4 kilonewton, the design capacity for one screw. And of course, now we can see how many screws we can put into this timber member, and it's just for this width of 140 millimeter, we can just use one pair of screws, one cross in that sense for this 130 millimeter width that we would need. Yeah, 4 screws would be actually too wide. So the total capacity here in this case would be around 12 kilonewton for this one pair of screws in this joint configuration. If we would put actually 2 screws facing in one direction, then we could actually benefit from this shear, or like the friction between the members. We could get a bit higher capacity for one screw, and also for the 2 screws we have around 15 kilonewton. So that might look kind like this. We could also then, in this case, of course, depending on the size of this main beam, we could actually place the screw here a bit to the back, so that we can benefit from a longer effective length of the screw. So in the ultimate case, sorry, that it's wrong here. It's square root of 2 times 180 millimeter, which is, I don't know, I don't have my calculator here. It's around, I don't know, 1.4 times 180. Anyway, in this case, the withdrawal strength, or this withdrawal parameter, actually is a bit smaller due to the larger lengths, but the total withdrawal capacity is of course much larger. Even for this slightly lower strengths, we get still quite larger withdrawal capacity per single fastener. We should also check, and that becomes relevant here, especially in this case, check also the tensile capacity of the screw. So in our case, we have the 800 Newton per square millimeter, and from the inner core cross section of the fastener, we can actually calculate the steel capacity of our screw, and that's around 30. So that's bigger than the withdrawal capacity. So we are more or less on the safe side that the screw won't fail before. Yeah, thanks a lot. It's 250 millimeter here approximately that we can benefit. So it's roughly 2 times, or 2 times the thickness, of course. Easy. So in this case, we can again benefit from the from this where did I there must be somewhere an error. I have to double check the results or the numbers here again. Of course, for these 2 screws arranged like this, we can again benefit from the friction here in the no, it's true. Yeah, we can benefit from the friction here in the joint line, and we have a total capacity of around 22, and a design capacity of around 15 kilonewton. And then for the 2 screws arranged like this, we have around 30 kilonewton actually that we can utilize here with this more optimized arrangement of the screws in the cross section. Maybe some words regarding the arrangement of the screws. So here you see these minimum spacing and end and edge distances of axially loaded screws according to Eurocode 5. And actually the spacing here is, I would say, rather maybe conservative, or of course it's maybe not optimized really for or I mean, it's kind of a general conservative values. So if you go to a specific manufacturer of screws, you can often find more beneficial values, especially, for example, in this case, when the screws are crossing, because of course, the intersection here of the screws, actually, yeah, the screws just intersect at one single spot, and you can actually reduce the spacing between the screws at this intersection point. So for here, for some screw diameters, actually, yeah, the A2 is around diameter 3 times the diameter. That's or this edge distance is actually the same as in Eurocode, or slightly smaller than in Eurocode. But actually, this spacing between the screws, if they are crossing each other's, that's then just 1.5 times d. So you can actually put them very, very close together in this situation. And yeah, between pairs of screws, you have a little bit kind of 3D spacing here in the situation. So what that means is that with a very product-specific screw, you can, with this more specific spacing of the screws by the manufacturers, you can actually put more screws into this connection, and you can reach a much higher load carrying capacity compared to the very general values that are given in Eurocode 5. So that might be actually beneficial for the design. Let's see. More questions. Yeah, I mean, there was this question about the edge or the spacing and edge and end distances by manufacturers. Of course, I mean, if you do a very general design, it would be probably wise to refer to the spacings in Eurocode. But if you do a more specific design where you maybe have already, or where you specify maybe some specific products already by a manufacturer, then you can of course use this more specific smaller values given by the manufacturer. You might also want to compare maybe different suppliers of screws. Typically, their specific values are very similar. So they are more like typically they are quite similar actually. So yeah, once you choose maybe, or you could recommend maybe different products from manufacturers where actually the values are quite similar. There was a question. I will post also these solutions here on Canvas so that you can find them, or you can go through them afterwards. It's again about the beam and column connection. But yeah, IFA has so in LIM Handbook Part 2, you can have a look.
There is an idea or a model for how to design that, but not an example, and I'm trying to find more information. So I'm right now going through the LIM Handbook here and try to find more.
Yeah,
The part 3. But I will post it then in also in written here if I find more.
Mm-hmm. Okay. I think I mean we can take also a small break. I think it's I don't have anything more to say from my side, but of course you can continue ask questions. Maybe you can have a small break and then continue, or if I don't know how many more questions are coming up and how much we can or if we have answered most of it already. So I will probably definitely go silent for 5 minutes or so. I don't know if or if I think we can return in at maybe 20 past 11, if that's fine.
I think it would be good to have a short break. So if we everybody's back at 11:20, then we can go on.
Yeah, okay. Then see you in a minute or some. Yeah. 20 past. Yes, hello. I am back. I don't know if you all are also back again. Maybe one comment here to this example of the beam to column connection that is here given in the Limtre handbook, and that might maybe create a bit confusion, or maybe why maybe the design is done here like this. Of course, it depends a bit which forces are actually acting on this connection to consider which which forces this connection has to be designed for. In this case, actually, it was assumed that you have all different types of horizontal and vertical forces acting, or that needs to be transferred between the beam and the column. And of course, these forces then will create forces or in the different fasteners, and create also a moment of this long steel plate that transfer the forces from the top to the bottom also, or vice versa. So depending, of course, if you only have a vertical force acting on the beam that has to be transferred into the column, then you could easily transfer this force via compression between the two beams. If you have a horizontal force, it needs to be, for example, transferred from the column, from the facade, for example, some wind action from the facade to the beam. Then you might need to choose a different alternative. For example, this steel plate, where actually the fasteners then transfer the horizontal force, for example, from the facade to the beam, to some other stiffening or bracing devices in this system. This connection here, when you have this eccentricity, then of course the forces per fastener are actually the horizontal or vertical forces equally distributed, plus the forces arriving from the moment, which are then determined from the moment divided by the polar what's called polar moment of the fasteners in the connection. And like this, the equilibrium or effective forces can be determined. There was one question about the because I showed this example here with stresses perpendicular to the grain, and of course one could imagine that if you have a small screw drilled into the timber member, and you pull out this screw, that actually you might, or that would be a similar case of this failure mode. But of course, for a single screw in a large timber member, you can of course also benefit, or practically actually, from a very large width of the timber member that is contributing to the load carrying capacity of this screw in the timber member. So I would say for especially screws that are used just for fixings, for single screws, that is normally not an issue. If you attach here some kind of angle bracket or some steel member with a larger number of screws, then this will become often decisive, or the splitting might become decisive, since the large number of screws actually then introduce a quite high force into this timber member. But for a single small screw, it's normally this can be often the splitting can be neglected in that case. So if you just use one screw to fix the cable or some other fixing here, that is commonly not a huge problem.
I have one more comment about the splitting. If you want to prevent splitting, then you could also, if you have the possibility to have something which goes on the top, over the top of the main beam that you want to hang something in, so that it's actually not that you don't introduce tension perpendicular to the grain, but that you have a compression perpendicular to the grain on the beam top.
I mean, here this
picture, and I think that's a good solution quite often, but then it's difficult maybe to do it afterwards. But if you know you need to hang in heavy equipment, heavy lighting equipment or so, then you could do it like this. Also, it's possible to do it for, if you have secondary beams, then you can have beam hangers or bulk skew, which are connected and they go over the top of the main beam if you have secondary beams from both sides. So I think that's always a good solution to change it from tension perpendicular to the grain to compression perpendicular to grain.
Yes, it's very. I just looking for one. And here's also an example of a secondary beam connection. For example, here, this, or do you see my browser? Maybe. Already synced. So here in this case, actually, you have a secondary beam that is connected here also with a steel member to another column or beam. And in this case, of course, the fasteners are located rather in the upper part of the beam. So you of course have this H effective, which is rather small, and it's not very beneficial. And you will expect the crack to occur here at this row of fasteners. So it would be of course good to place the connection here in the lower part, where then you can of course have a much larger H effective. But here actually there's also some reinforcement, for example, a large screw that is going here over the entire length of the beam is used to reinforce this this joist hanger here so that this splitting force is here actually taken by the reinforcement in that case. So that is, of course, also possible.
Det kommer en fråga precis här om vi bara svarar på frågor om förband just nu eller om även andra frågor som ligger på Canvas. Vi ska också svara på de här saker som ligger på Canvas om vi hittar dem. Det är ibland lite svårt att hitta exakt var det ligger nya frågor. Jag vet inte om jag tror Robert det var I think Robert that was the one you had you said you could answer.
Sorry. Yes. What?
I think there was a question on Canvas earlier.
Yes.
I think it was about DLT and connections or so. Could that be the question?
Yes. One was related to slotted in plates. Yeah, I mean, if there are holes already in the slotted in plates, and I mean there are both solutions. I mean, typically for the simple smaller joist hangers, or often they are pre-drilled, or they are drilled with these dowels. But for larger connections, actually they are so here you see this pre-drilling or self-drilling dowels, for example. You can create also a truss connection here. I think what I don't know if they have a steel plate thickness. Yeah, of maximum 10 millimeter for one plate, or otherwise 5 millimeter per steel plate. So that is one solution. And of course, in other cases, there was I don't know. Where did I have it? Here some example of aluminium steel plate, or the aluminium plate for here main beam secondary ribbing connection, where then the dowel is actually drilled through the steel plate as well. There are these other examples of I mean, just to show here from one producer, where different solutions are provided here, for example, with also pre-drilled holes already in the plate, where you then of course have to fit the holes in the beam to this hole pattern here. And maybe here also one example of slotted in steel plates that are of course currently not drilled by hand but by CNC machines, so that you can actually have a very precise pattern of the holes, so that you can assure that the whole pattern is actually exact and does not deviate or is not a bit tilted, or is nicely straight in the beam. So there are different possibilities. There was one comment or the question on the to calculate the shear stresses in the CLT panel. Of course, we have this situation where we actually have we have this combined cross section of layers of different stiffness, and of course we can calculate the bending stresses, tension and compression stresses in this cross section, assuming like the effective moment of resistance here. So we disregard the cross layers which are loaded perpendicular to the grain due to their low stiffness, and we just consider the layers parallel to the grain, loaded parallel to the grain. So in the different direction, the resistance or the bending capacity is different for these types of solutions here. When it comes to the shear stresses, then it becomes maybe a bit more a bit more difficult, or it's not so straightforward to calculate the shear stresses of this combined cross section. So you need this S, the static moment, the E again. You can derive as similar to the as for the bending case, and depending on the axis, so in the layers that are loaded parallel to the grain, actually you have also a rather high shear stiffness, or the shear stresses increase in these layers. In the cross layers, they are very soft. Again, you don't really have a real increase in shear resistance or shear stress, and so you kind of account mostly for the layers parallel to the grain. So in this direction and in the other direction, you actually also have different shear stress distributions in your cross section. What should you maybe consider? That of course each of the layers, or like the parallel and the perpendicular to the grain layers, also have a different shear strength. So in this case, the highest shear stress is in direction parallel to the grain. So you have the normal shear strengths, and in the cross layers, then you have just lower rolling shear strengths that you can consider. For the other case, in the other direction, yeah, you have actually the highest shear stresses also in the layer with the lowest shear strengths, where you have the rolling shear acting. And of course, that might be maybe yeah, a relevant case where you might have observe the failure. Regarding this static moment, the equations are given here a bit before. So in the you sum up the stresses or the depending on each layer, the stiffness of each layer. Actually, you can calculate the S in the two directions. In the one direction where we have more layers loaded parallel to the grain, and in the other one where you have less layers and yeah, more perpendicular to the grain layers acting there. A safe choice might be to disregard the stiffness or the layers perpendicular to the grain. Like that, you can or it might be an easier calculation than for the shear stresses. Yeah, that's for the stresses here. The question about the screws in CLT. Well, I mean, I don't know if in here there are some recommendations for the screws in CLT given. What is the withdrawal capacity is slightly different from okay, here it's the same withdrawal or like a bit different withdrawal capacity given here. So that, I mean, you can more or less calculate it like that. I mean, in the how it's called in the face or the side face. Anyway, the screw is more or less perpendicular to the grain always. On the edge, of course, it could be perpendicular to the grain or parallel to the grain. Yeah, you have to, based on your geometry of the CLT, you then have to decide also or choose where to put the screws and how they are, in which direction they're acting actually. But I mean, with that you can more or less calculate it. This I don't fully understand the question. Okay, if it's self-drilling wood screws, well, I mean, it's I mean, I would say in CLT, more or less only these self-drilling screws are used, or I mean, in I would say in 99% of the timber engineering or timber structures nowadays, these self-drilling screws are used. So that would be, I would say, definitely the choice to take. Maybe I don't know if I can have a quick, wait a second. So maybe one general comment on the types of screws. Or I mean, these are more the traditional wood screws actually that are maybe can be considered as an alternative. So I mean, you have these traditional screws where actually the thread of the screw is cut into the steel or in the wire of the screw. And these screws you typically have to pre-drill along the shaft with a shaft diameter, and here with a smaller diameter, basically. But these more or less self-drilling screws, how they would be, or self-tapping screws, you typically do not pre-drill in most applications. So up to around, yeah, there are screws, or some screws are up to 13-14 millimeter thickness. And depending on the application, you do not pre-drill these screws. There are some more threaded rods with a wood thread, actually. These ones you would pre-drill since they don't really have a drill tip with 16 or 20 millimeter diameter. But up to 14 millimeter diameter, you basically do not have to pre-drill. And they typically have a drill tip also to screw them in without pre-drilling in that sense. So that's probably and there was something said for screw spacing. Let's have a look there. I hear some spacing of screws in CLT. Yeah, I mean, I would say the most I would say the screws that are used for engineering purposes in a way are typically larger than 8 times or 8 millimeters. So there are some example maybe of I think some maybe 6 millimeter screws also available. But yeah, I mean, if you so these types of screws are typically used for CLT structures. Of course, if you have a smaller diameter screws that are, for example, used together with steel plate or like fixings or to hang up some steel plates, for example. Let's have a look. And we have here this I mean, if you connect here some angle brackets, for example, to a CLT or other types of structures, yeah, you also use smaller screw diameters. In that case, well, I mean, one would use, of course, spacing by the manufacturers. Or I would assume that also these rules could apply. I have to double check. Alternatively, I mean, the small screws actually could be considered as nails actually. I don't know which one would be here more conservative. I think some in some cases actually the nails in some situations are more conservative for the small diameter screws. So small screws are more similar to nails, so that could be chosen here. I don't know if the sound is okay or if there's some issues.
It's okay for me, at least.
Okay, I was maybe not talking too clear, so that might be the reason for the poor quality. Yeah. Yeah, I don't know if I hope we answered almost all questions. I have to see. Oh, there was one last. There was one last question on Canvas about the preliminary design of the stabilization for this Scherm socket. If I take it correctly, then of course you have to either, I mean, if you have a horizontal load, then you should like carry this horizontal load with your somehow in your system, and either your pillars or columns are clamped in the ground, and so you have a moment rigid connection in the column foot that carries or that can carry the horizontal forces. Or of course you have to find a suitable bracing system to carry these horizontal loads. If you just have vertical loads, of course you also should assure that your buckling resistance, or you have to of course have some bracing, or depending on your system, you might need also some bracing system to carry your buckling forces, or the forces to brace the buckling. Yeah. Okay. Yeah, I think we can or give a short, or also write a small answer to these questions. Maybe in the, I don't know how it was with the others, but maybe in the recorded version also, of course, there will be a better sound quality, or maybe that might be better. So some more administrative questions can be probably best answered by Patrice, who has an overview.
Det kom precis en fråga kring inspelningarna. Det har varit svårt att lägga upp dem på Canvas. Patrice, vet du när de kommer ut på YouTube?
Patrice här, hör du mig Eva?
Ja, jag hör dig.
Ja, just det. Så det blev på Canvas, jag tror det är någonting med utrymme. Jag försökte gå på deras hjälp och där stod det att de rekommenderar även de som har Canvas på universitet att efter en viss kvota så ska man ladda upp på YouTube och sen därifrån länka till kursen. Och det här fick jag reda på, för det är tre inspelningar som jag tyvärr inte lyckades få upp på. Och nu fick jag det svaret av dem att de rekommenderar samma sak om man har. Jag frågade till och med om vi kunde köpa extra kvota, men de har inte den optionen. Så jag får se till att ladda upp på YouTube och därefter länka. Och det är en av de flera saker jag kommer att göra under den här helgen. Så det borde vara tillgängligt under helgen på måndag.
Men jag tänker också, vi kan ju försöka ge ett skriftligt svar också på dem. För jag har skrivit in lite svar under tiden här. Jag tänker om vi sammanfattar det, för det var ju ett antal diskussioner som återkom om vi försöker i alla fall ge svar
vi
på
gjorde
de här
så
viktigaste
i första veckan där med Roberto. Vissa frågor svarade vi på papper och så laddade vi upp det på. Så det kanske vi kan, Robert, maybe we could do the same with some of the questions, just as we did during the first week. Maybe not all of them, because then it's repeating the same work. If there are some questions that you feel that you have not answered, then we answer them on paper and upload. Because by this weekend, I will create the YouTubes. I have never uploaded something on YouTube, and our ET support usually want at least 1 week if you order something from them, and I cannot wait until the end of next week for them. So I will try to do it myself.
Yeah.
So if there are some questions you feel you haven't answered properly to, we try to and do it, and we upload it on Canvas.
Yes. Yeah.
Okay.
I mean, there was a question here. Where when the project orders.
I've answered that to all. I think because maybe I wrote it wrongly. I wrote in the email that we will start checking the partly submit those submissions during starting the end of this week. But maybe it was understood that we will answer, or I wrote. I don't remember what I wrote in the email, but it's about half of the attendees that have submitted. That's 40, and you need at least 1 hour, 1.5 pair. So there is no way I start today and I will be able to answer to everybody now. So I told them in order of submission, I will start senaste på fredag nästa vecka får alla svar. De som har laddat upp först får naturligtvis granskning först. Så det kan hända att några får redan på tisdag kanske. Men det är 40 personer runt som har laddat upp någonting. Och det tar ju 1,5 timme, 1 till 1,5 timme minst att göra en snabb granskning. Så det finns ingen chans att man skulle hinna. Det är 1,5 arbetsvecka. Och ni laddade upp färdigt i måndags. Och vi har ju lärare andra arbetsuppgifter. Det är inte det enda vi gör. Så håll ut med oss. Nästa fredag får ni feedback. Ni som har lämnat in. Och det var också frågor om quizen. Jag har svarat också där. Att det är första gången alla vi lärare gör quiz på den här plattformen. Men det blir ungefär 70% av frågorna ska man svara rätt. Och så har man möjlighet att göra om det 3 gånger efter första försöket under en vecka. Har man fortfarande inte gjort det, vi måste ju också stänga kursen någon gång. Så vi måste ju stänga den i oktober. Har man gjort totalt 4 försök på quizen och fortfarande inte fixat det, då är det i januari, februari där när nästa kurs ges. Då får man göra det vid det tillfället. Så det var de 2 administrativa frågorna som vi hade. Jag ska se här, någon frågade om inte slutinlämningen var nästa fredag. Jag kommer inte ihåg, ursäkta mig, jag måste bara titta snabbt här. Var det inte under vecka? Jag tittar här, vad hade vi skrivit? Deadline inlämning projektarbete, det är om knappt 2 veckor. Fredag 16 oktober klockan 23:59. Och för de som har redan gjort tillräckligt mycket hittills så kanske det är bara förband som är kvar att göra. Så min bedömning är att ni har tillräckligt med tid att kunna göra det till fredag 16 oktober. Är det svar på frågan? Det står på kursbeskrivningen, kursprogram, sista sidan. Vecka 42, fredag 16 23:59. Vill ni det kan jag förlänga det till söndagen, men jag vet inte om det är någon som tror att ni behöver helgen också. Normalt, så som vi har, det här är ju en projektuppgift som är anpassad till er som är yrkesverksamma. När vi har motsvarande typ av projektuppgift så tar det ju en hel period, en halv termin för studenter i sista året på 3-åriga högskoleingenjörsutbildning eller på master. Då brukar de göra 15 HP en projektuppgift, men då gör de mer än vad ni har gjort. Så vi har försökt fokusera det här på att ni ska bara göra beräkningar på trä. Och som jag har sagt flera gånger och skrivit i projektbeskrivningen, så var meningen, om ni kan och har möjlighet till det, att inte lägga för mycket tid på första delen, strukturanalys och lastnedräkning. Och det var fritt för er att använda dataprogram. Det stod i projektbeskrivningen, och jag sa det också i början på kursen. Jag sa det när jag presenterade projekt för 3 veckor sedan kanske. Ja. Okej, någon skrev att ni behöver helgen med. All right, då får jag flytta 2 dagar till om det hjälper. Okej? Fler frågor om projekt? Uppgiften, om quizen, om något annat som har att göra med administrationen. Vad händer om man inte blir godkänd? På vad? På quizen har jag svarat tidigare. Man får testa. På projektuppgiften. Okej. Men vi ger ju er feedback när ni har lämnat in. Får se, vi har medvetet lagt in att kursen slutar vecka 44. Tror jag. Låt mig titta igen på 2 veckor efter inlämningen. Jag försöker hitta kursbeskrivningen. Ja, jag står här. Vecka 44 är kursen avslut och diplom. Och vi gjorde bedömningen att det kanske är några som får komplettera någonting. Och därför har vi den marginalen på ett par veckor innan kursen stängs. Så är det här är en konstruktionskurs är ju ingenting som är som matematik. Det är inte rätt eller fel. Exakt samma byggnad kan 10 konstruktörer räkna på 10 olika sätt och alla uppfylla Eurokodkraven. Så vi tittar ju kvalitativt på vad ni har gjort och bedömer hur ni har dimensionerat och rimligheten och allt sånt. Vi kommer inte att gå på kilonewton-enheter och se om det är rätt eller fel. Det är inte på det sättet. Det är en kvalitativ bedömning. Men är det mycket fel, då får ni feedback och då har ni kompletteringsmöjligheter någon vecka där innan kursen stängs. Men förhoppningsvis. Och de som har redan lämnat in delinlämningen kommer ju att få mindre anmärkningar på slutinlämningen, tror jag. Så. Fler frågor? Okej, det verkar inte vara några fler frågor. Då tackar vi för att ni har visat intresse och engagemang. Ungefär 60-70% av er har varit med på även alla questions and answers. Och vi förstår ju att ni är yrkesverksamma och har andra arbetsuppgifter, men det är första gången vi gör kursen på det här sättet och vi kommer säkert också att lära oss och för att göra det bättre. Men vi har förhoppningsvis anpassat kursen så mycket som möjligt till yrkesverksamma. Våra samarbetspartner, jag vill inte säga konkurrenter, från Stålbyggnadsinstitutet har en motsvarande kurs. Den är på 3 hela dagar plus en tentamen. Och vi har försökt, vi tyckte inte att tentamen skulle passa utan quiz plus en projektuppgift passar bättre, tyckte vi. Ni får lämna synpunkter sen i slutenkäten om ni tyckte det var bra så eller om det hade varit bättre att man gör som Stålbyggnadsinstitutet med en hel tenta en hel dag och sånt. Så vi är tacksamma för alla synpunkter. Det kommer en survey på hela kursen senare. Ja, svara gärna på Pauls-frågan, mejlat in, så det här. Okej, vi ska titta på mejlen senare. Vi kommer att fortsätta ända tills kursens slut att svara på mejl på Canvas. Jag brukar försöka svara direkt i Canvas. Och sen under diskussionerna kommer Eva, Robert och jag att vi försöker en halvtimme varje dag kolla upp om det är någonting som vi behöver svara under diskussionstrådarna. Roberto, som jag har meddelat tidigare, är pappaledig, så han kommer inte att vara tillgänglig på samma sätt. Men vi fortsätter svara och stötta er under Canvas. Så om det inte är några fler frågor så får jag tacka för den här gången och önska en trevlig helg, och sen kommer fortsättningen med quiz och inlämningen av projektuppgiften. Så, trevlig helg allihopa. Eva and Robert, do you want to add something?
No. Have a nice weekend.
Yes,
same to you.
good day.
Yeah, okay, thank you.
Bye bye.
Robert, do you stop it so I will also try to put it on YouTube? I will download them.
Very good.
So there are 3 or 4 videos that will be uploaded to YouTube and linked to the course.
Yeah.
So you stop recording. I think you were the main presenter today, right?
Yes,
Or you end it or something, and then that's it.
I can stop it